So continuing here with the olfactory system, a little bit up closer right here, so you can see the olfactory neurons. Here's your olfactory epithelium right here. These are the sensory cells, and here we're going through we're going to go through this ethmoid bone, these olfactory foramina, and we're going to synapse right here, and this is the olfactory bulb already. So very close proximity, very fast kind of nerve conduction. And then we're just going to continue on here for evaluation. Here even more up close right here. So you would have here, these are the chemoreceptors right here. These are all G protein coupled receptors, and then we have receptor potentials, and we're going here through these olfactory foramina and then toward the olfactory bulb. And as I mentioned earlier, there's this link between smell, memory, and emotion, and it's actually pretty strong. If you think about it, I'm sure you've had this experience that you smell something and it brings memory back from an event where you smelled a similar scent or the same scent, and it just brings the memory back of the events and what happened during the time, and sort of emotional kind of responses as well. So the olfactory sensory neurons, of course, they're in the olfactory epithelium in this nasal cavity. They're all G protein coupled receptors. Okay. Gustation, that's your sense of taste, and we always think that our sense of taste is so great, and really it's not. It's really what's the powerhouse is olfaction. The olfactory epithelium is much better in distinguishing fine nuances of different odorants, and so what you think a lot of times, what you taste, actually you smell it. So when people think about it, when people are going wine tasting, they don't taste the wine, they put their noses in their glasses and swirl up the aromas, and then just put, get everything into their nose. Well, because they're not really tasting the wine, they're smelling the wine. And so the reason why we like to smell things and have a much better ability to distinguish different kind of scents is because our olfactory system is just so much better than our tongue. So in the tongue, we have basically 5 sensations, very basic. Just sweet, sour, salty, bitter, and umami, it's like a meaty kind of flavor. And each one of them has a receptor, of course, and then you're just gonna do this taste transduction via sensory neurons, of course. Let's take a look at what this looks like. So here's your tongue, and you might have noticed that your tongue is kind of rough on the surface, and it has these papilla, these taste pores. Anything that you want to taste would have to be dissolved in saliva, and then it would have to enter the taste pores right there. Here's a diagram that spells it out a little bit better. So we do have sort of a regional, a little bit stronger ability to taste on here. Let me draw this on so this here is the traditional kind of view that if this is your tongue, the front here is best suited for sweet. Then on the side, we have more perception for salty and sour. And on the root of the tongue, that's your prime spot for bitter sensation. Now, that's not entirely true, because you can see here on this taste bud, it has pretty much all the different sensations that are possible. But classically, and maybe if you tried that out last week, you might have sensed that you do have a little bit better sweet perception in the tip, and a little bit better for salty and sour on the side, and a little bit better for bitter in the back. But here's sort of a taste bud that has all the different types of receptors. So here would be sweet, the sweet receptor, that's a chemoreceptor. Umami is also chemoreceptor. Here another chemoreceptor for bitter. And then we have sour, and we're salty. salty right here over there. This one is salty, sour. They perceive hydrogen ions, H plus hydrogen ions, and salty. They will respond to sodium ions. And we'll take a closer look. So here there will be for sweet, umami, or bitter. These are all the chemoreceptors. They're all G protein coupled receptors. And the signal transduction. So once the chemical is received by this sensory cell right here, so it's a G protein coupled receptor that this molecule will bind to something sweet, for example, or something bitter, and then we're going through a second messenger pathway that opens calcium gates, and then in the end we just need to fire action potentials. That's here with this lightning rod, and then we are going to evaluate this perception. Sour is perceived through hydrogen ions, salty as well. So here basically the hydrogen ions, they carry a positive charge, seems true for sodium ions, and they will alter the membrane potential, and then you release some neurotransmitter here, and that causes an action potential to be fired here at this secondary neuron. So here in steps, basically, we can keep this pretty simple. But keep in mind, sweet, umami, and bitter, those are G protein coupled receptors. These are chemicals that will bind here to these G protein coupled receptors, and then in the end, we're firing action potentials here. And then here, over here, sour and salty as well. Those are cations, positively charged ions, either hydrogen ions or sodium ions. It looks the same. And they will alter the membrane potential, ultimately leading to the release of neurotransmitter, which then results in the firing of action potentials, APs, action potentials. And here finishing up the same thing. So here the neurotransmitter was released, and now it's causing these action potentials. I think you get the idea. So sweet, umami, bitter, these are chemicals that bind to G protein coupled receptors, and then sour and salty, sodium ions, they will alter the membrane potential by opening or closing ion channels, basically, and that either way it leads to action potentials on these primary gustatory neurons. Moving on to the ear, our sense of hearing. Here's an anatomy picture that you should review if you forgot everything about the ear. So we're funneling these auditory signals here through the pinna of the ear, and then here we have the outer ear canal. The tympanic membrane will then convert these mechanical waves into a vibration that causes the three ear ossicles, malleus, incus, and stapes, to vibrate, and they're basically using the little stapes right here. The vibration of the stapes will cause a vibration of the oval window, and then we get the signal into the inner ear, and this looks like a snail house, the cochlea right here, and then we have hair cells inside there that will be bent, and that's will cause an action potentials to be fired or not fired. So let's take a look. The perception of hearing, we have sound waves, and these are mechanical waves. The frequency of these waves is the pitch that you perceive, and the loudness of a sound is due to the amplitude. How tall are those waves? So let's take a look at this. So these sound waves, they have a certain wavelength, and again, wavelength, they have both an amplitude and a frequency. The amplitude would be the loudness of the sound, and the frequency is the pitch that you perceive. So here's some more information about wavelength. You can take a look at that. But here, so these sound waves, they will enter your outer ear canal, and then they will hit the tympanic membrane, and that sets it all in motion, because now these middle ear ossicles, they will start to oscillate and vibrate, and then the oval window will start vibrating, and that vibration is then transmitted into this gelatinous fluid right here in the inner ear, in the cochlea. I'll take a closer look at that. So here steps one more time. So we have the outer ear catching these sound waves, then the vibration of the tympanic membrane that ultimately leads to a vibration in the fluid of the inner ear. And depending on the pitch of the sound, it always enters up here in this upper chamber right here. That will be the vestibular duct, and we're entering right here, and then we're turning around depending on the pitch of the sound that was perceived. So here in steps, you can read through that. Okay, so now let's take a look at what happens inside of the cochlea. If you were to stretch out that snail house and make it, straighten it all out, you would see that there are 3 layers basically. So you have an upper duct and a lower duct and a middle duct in blue right here. If you take a closer look at the middle one, so then you here have this window right here, this will be the middle duct, and you get it even up closer, then you will see that the hair cells are embedded into this gelatinous material right here, and they have a roof on top of them that's called the tectorial membrane. The tectorial membrane is linked to the tallest of these stereocilia, these little hair that are sticking up from the receptor cell. And once the vibration comes along, then this roof of the tectorial membrane will also start vibrating along with the bottom here, which will also start oscillating. And so this would be the basal membrane right here. And so all of a sudden you have this minuscule kind of yanking on these hair cells, bending them one way or the other. And that causes the opening and closing of ion channels, and that ultimately sends the actual potentials, which you then use to evaluate what you have heard. So here, another anatomy summary picture. So keep in mind we have these 3 layers or ducts basically here. So the vestibular duct will be the upper chamber right here. The tympanic duct will be the bottom one here. The basal membrane is this portion right here, what I'm just drawing here in blue. And then the tectorial membrane is sort of the upper roof right here. And then in the middle you have this cochlear duct that has then the hair cells, the actual sensory cells. We do have this gelatinous fluid. In the vestibular and tympanic duct, we have perilymph, and then the endolymph in the cochlear duct. What's important for the physiology is that the cochlear duct contains the organ of Corti, which is what I just pointed out with the hair cells to you, and I have a more up-close picture coming. So in the organ of Corti, we have these hair cell receptors. These are the actual receptor cells. They sit on the basilar membrane, and then they have this roof that's the tectorial membrane. And once everything starts vibrating, then we're bending those hair cells. But let's take a closer look. So here, the 3 chambers. Here one more time. What's important here is this one right here, this section right here, the organ of Corti, where you have the actual hair cells, the sensory cells. So up close right here. I like this picture. This diagram makes it pretty clear. So we have here the basilar membrane, tectorial membrane right here, hair cells right here. These stereocilia, they have different lengths. Can you see that? So this one is really tall, and it's connected to the tectorial membrane. If the tectorial membrane starts vibrating or shifting, it will bend these hair cells. You see how they're being bent down here? And because the tallest of these stereocilia is connected to the tectorial membrane. So now this bending of these hair cells will open and close ion channels, which then ultimately leads to actual potentials that then get transmitted via cochlear nerve to the brain for evaluation. And so here is sort of the summary of this happening. Depending on which way these stereocilia are being bent, they're sending more or fewer actual potentials. So here is baseline, no bending at all. And note how these stereocilia, they are linked to one another by these tiny little springs. They're just all this little spring, a little connection right there. that's holding them together. So when the tallest one is being bent, it's going to pull the other ones along with it. So if we pull in this direction on the tectorial membrane, then the tallest of the stereocilia will be bent to the right.